Hello. Sound is going.
Yeah, we are able to hear.
So now we are having parallel session P2, and let us introduce judges. So judge 1 is
Session coordinator, Dharmen Sharma.
yes. PPT खोलना चाहिए. Yes. How to make it in large?
What is it?
So our first judge is Dr. Sanjay Malhotra. He is an outstanding scientist from 30th batch, 33 batch, and presently he is head of electromagnetic application and instrumentation division at BRC. His specialization is electromagnetic design. इसको बड़ा करो. बड़ा करो. He is specialized in electromagnetic design and engineering development, and worked on electromagnetic design of RF cavities, beam handling devices, and accelerators for accelerator and RF devices. He has developed and deployed magnetic flux leakage based inspection tool for in-service inspection of transportation pipelines. He has pioneering contributions towards Indian institutions Fermi Lab cooperation. He is recipient of several awards from academics and research, including Young Engineer Award for Indian National Academy of Engineering INAE and Homi Bhabha Science and Technology Award, and also Group Achievement Awards. Our next judge is Sri PC Saroj. Desktop पे ही था. वो आ रहा था desktop पे. हाँ. Yes. Mr. PC Saroj is presently working as project manager, EBC, BTTG, BRC, and involved in development and utilization of EV facilities, RF and DC both, at Electron Beam Center, Kharghar. He designed and developed multi-gigawatt pulse power systems for for strategic and nuclear applications, 40 to 100 kilojoule electromagnetic manufacturing equipment for forming welding applications, for tube plug joint for PFBR applications, fast trigger generator to synchronize spark gap switches. He has played a key role in transferring various technology through TTCD, BARC. He is recipient of 4 DAE Group Achievement Awards and DAE Scientific Technical Excellence Award for the and he is authored around 54 papers, and he is member of many scientific and engineering societies. Now, let us start the presentation. So, one request to participants: this time is 3 minutes. Strictly, it has to be followed, and 1 minute is for question answer sessions. So now let us start the first presentation. अभी जो है वो ट्राई करो पहले सच लिस्ट ये है बट कविता मैडम का पहले करेंगे तो म्यूट करते हैं
Hello, can you hear me? Hello?
Yeah, we are able to hear.
Can I start? You will be sharing the PPTs? If there is problem, can I share the PPTs myself? Okay, fine. Can I start? Sharma ji, can I start?
Please start, madam.
Yeah, good afternoon to everybody. I'll be talking on the investigation of failure modes in the RF power system of the 10 MeV industrial RF electron LINAC. And it is co-authored by my colleagues in Reactor Safety Division, Mr. Vipul Garg and Dr. Gopika Vinod. Can we have the next slide, please? Yeah, the RF power source per se consists of the from the AC power, we go through the line type modulator, and then we are feeding it to a klystron, which is a driven system with from the amplifier and the driver, we get RF signal for the klystron. And through the waveguide plumb line, which has a circulator, the directional coupler, and other waveguide components, and the RF window, we are feeding it into the LINAC. And the specifications of the RF power system is that it can handle and deliver 6 megawatt of peak power, 24 kilowatt of average. And the RF power input is about 70 watt from the amplifier. The filament heating is about 800 watt for the klystron at for 26 volt. And we are having the cathode voltage at about 55 kV. Current is ranging from 270 to 280 amperes peak, with pulse width of 10 microseconds and rep rate, which can be varied from 5 to 10, 400 hertz. And you have the pulse rise and fall time being 0.5 microseconds. The aim of this study is to study the faults in these systems. So various faults indicated here. The fault tree, which talks about the vacuum failure, the increase in the SF6 or the decrease in the SF6 pressure, which can lead to the breakage of the tube in case of increase, and for decrease you will have the
1 minute left.
breakdown, electrical breakdown. Pardon me?
1 minute, please. 1 minute more.
Okay. So you have various faults which are contributing to the power failure of the RF power source. Similarly, we have the fault. Next slide, please. The fault modes and effects analysis again goes through the various modes of failure and the detection mechanisms and the effects, both local as well as global. So what we, next slide please. Here the highlight is on applying these techniques to the Bayesian network, where we are having the RF power source failure as the top event and various other events. And here we are putting in probabilities where these are the independent nodes, and the ones in black are in the independent nodes. And when we feed in the data from the operational data from the 10 MeV, we're able to get probabilities which we are feeding into this network, and the Bayesian network is able to predict the failure. So you can see here that given the operational data, we are able to get about 6.3% failure chances are predicted for the RF source. And same thing, we can use evidential reasoning as well as the reverse reasoning to estimate that if there are certain faults and the rate probability of these faults, then we will be able to predict the fault of the RF power source. So this
So
is
now,
the,
madam, time over, please.
yeah,
This question
I
answer
think I
session.
any
So
questions?
any questions? Any online questions is there?
When will
So there are no questions. Thank you, madam.
Thank you
for
so
your
much.
presentation.
Okay, thank you.
Now we'll move on to next paper. But taking directly. 5-9. You can take 5-9.
so you'll be giving
Yes. Which? So our next presenter is Mr. Nausad Ali, and
paper you can.
Mr. Nausad, please, with paper ID 1059.
Yep. Okay.
Yes, your time is start now.
Yeah. Yeah. Good afternoon to all present. I would like to thank organized committee of Vstaa for giving this opportunity for presenting this experimental work. The topic of paper is magnetic pulse crimping of copper lug with significant improvements in contact resistance and leak rate. Now, cable is one of the important part of an electrical system, or we can say it is the backbone of any electrical system. So, joining of cable or the end termination cable is very important. If joining is not proper, then it can lead to the failure of the system. And it has been reported that 60% of failures are due to the cable joint failures. Now, conventionally, we have been using soldering and crimping by mechanical means for joining of cables. But here, one new technique that has been, that is in the progress, and people are recommending this technique for joining of cables, and this is magnetic pulse crimping. This magnetic pulse crimping, the name comes from this magnetic field is being used for this. And if you see the experimental setup, the machine is shown in the first figure. It consists of two circuits, the charging circuit and the discharging circuit. We can think of this charging circuit as power supply and the capacitor bank, which is charged to certain voltage, and then it is discharged through a coil. And this discharging of coil, of current through this coil, it creates a magnetic field, and then these currents are used in the job which is to be crimped. Here the crimping is of copper lug to the strands of the conductor. This technique is very useful in terms of the connection, that is contact resistance, and this uniform compression of lug with the conductor of the cable takes place. Another advantage is that there are no marks on the surface of the connector, which is normally seen in conventional mechanical crimping. The advantage we get it, the contact resistance gets reduced, which is the very important parameter. Because if the contact resistance is more, then the heating will take place and the failure starts from there only. This technique, it is very economical if it is carried out on a large.
1 minute left,
Yeah,
please.
yeah.
Yeah.
The important thing is that uniform compression takes place and there are the voids between the strands of conductors, they get reduced. Now this experiment was conducted on a 120 square mm cable that was aluminum conductor, and then we tested it for the contact resistance and the leak rate. We could achieve 8.1 micro ohm resistance with the magnetic pulse welding, and 11 micro ohm was through conventional mechanical. Also the leak rate was measured for magnetically crimped cable. It was we could achieve 0.1 millibar pressure. This is a background pressure, and 1.4 into 10 power minus 5 millibar liter per second was the leak rate. In mechanically crimped cable, this
Okay,
background could
please,
not be
time
achieved.
over.
Yeah.
Now it is a session for question answers. So any questions, please?
Yeah, Naushad, there is one question. This is Sanjay Malhotra here.
Yeah.
In a typical solenoid coil, the forces are in which direction? Largely?
Yeah, this force is this coil radially.
Radially out.
Yeah.
Oh, but here you are able to press that job as readily in. Can you explain why this happens?
The field shaper is being used here. That this magnetic field is confined to the job.
No, no.
Here, field shaper is one of the important equipment in this magnetic pulse
So
welding.
that accelerates. That I understand. I'm only asking why in the job the pressure is in the inwardly direction and in the coil it is outwardly direction.
No, it is if you are going for compression, the position of the coil and then the job piece, it is different. And when we are going for expansion, it is different. So in compression, the coil is, this job piece is placed inside the coil.
Okay, it is there. Okay. Sarojji, you want to ask?
So thank you. Now let us move to the next speaker. A. Siju, paper ID 1062.
स्लाइड चेंज करने के लिए नेक्स्ट बोलना है देन ओनली ही विल चेंज द स्लाइड अपना स्लाइड को चेंज नहीं कर सकते
So your time starts now. 3 minutes, please.
Okay, thank you. I'm Shiju from RFSS section of Accelerator Control Division, BRC. So I am presenting my work here. The topic is design and development of measurement and protection system for RF cavity. Next. This introduction, this system consists of one RF chamber. The RF chamber is connected to vacuum pump for generating vacuum, and the remaining sections are RF amplifier, directional coupler, and DC power supplies, and some other sensors for protection of RF cavity. So in that, means for protection, we are taking that the RF signals, and vacuum signals, and arc signal, and a temperature signal, everything. Next. So the hardware and sensor measurement to protect protect this accelerator cavity against damage. We are measuring that we are measuring and electronic. We are generated the electronic system, and excuse me, ये just निकाल सकते हैं क्या? Yes sir. Okay. Previous. For that, the sensor we are using vacuum measurement and temperature measurement and arc measurement, then RF power measurement, then RF controls, and the data acquisition system. This the temperature sensor we are using LM35 signal. Then for arc measurement we are using Honeywell photo transistor, and for vacuum signal that using the cold cathode sensors. Next. So the data acquisition system is taking the field signal to field signal to data acquisition system through through one isolator.
Please.
Okay, isolators. Then the data acquisition system consists of three analog signals and one digital signal and 5 digital output signals. For digital output signal, we are using the switching on of power supplies, and digital input signal we are using arc measurement, and analog input signal we are using for temperature, vacuum, and RF measurement. So that the picture is showing that the GUI in that we are made the GUI using LabVIEW 2017. Then the data acquisition we are using the NI based NI USB based 6009. That is a 48 kilo samples per second sampling rate.
So time over, please. Any questions, please?
Yes, I have.
Shiju, just one query.
Sir.
You have a different physical phenomenon you try to capture through data acquisition system, the temperature, vacuum,
Yes.
and RF signals.
Yes.
All do not change, do not have the same inertia, do not need to acquire them at the same rate. They don't change at the same rate. So how do you fix the sampling frequency, given these signals have different rates of light?
Okay, sir. As for data acquisition system, we are the frequency sampling rate is a 48 kilo samples per second. So we are taking continuously. We are taking the temperature, vacuum, and RF signals.
So it should be the fastest or the slowest moving physical phenomenon, which should be the guiding factor.
Actually, the temperature and vacuum that is the slow signals. We are mainly that fast signal. We are taking that the arc signal. So
Okay.
arc signal we are taking from a digital signal. So it is very fast.
So
Okay.
time over, please. Thank you. And next
Okay, thank you.
participant is next presenter is Shreya ji. Number 1070.
आप बोल रहे थे तो मैं बोल रहा था। हाँ नहीं आप टाइम बहुत कम बता दें। हाँ बहुत कम है इसलिए मैं भी
I cannot see my presentation.
क्या नंबर क्या है?
70.
So your time starts now. 3 minutes, please.
Good evening, everyone. So I'm going to present my work on thermal and structural simulation and fabrication of X-ray target for 6 MeV X-band LINAC. So basically, our division is involved with developing a LINAC, and it will be used for cancer treatment. So IORT, the radio surgery, for that it will be used. And it's a 6 MeV LINAC, and the frequency for this LINAC is 9.3 gigahertz. So it comes under in X-band frequency range. And one of the important part of that LINAC is the target, because ultimately for the treatment we need X-ray, high energy X-ray. And for that the target has been designed, and I have done the thermal simulation of the target. So I want to go to the next slide. So this is the target profile. So this, as you can see that there is a flange, SS flange. So this flange will be at the end of the LINAC, and we have a copper material also. So this copper is, because we know that the thermal conductivity of copper is very high. So like constantly the target will be subjected to heat load from the electron beam. So for removal of that, we need copper, and also we need to provide cooling, water cooling, for efficient heat removal. And the target itself is the tungsten target, and the thickness of the target has been decided by Monte Carlo simulation FLUCA. So we have taken the target thickness is optimum. From the simulation, we have decided the target thickness. Now the simulation result. So for this simulation, I have used COMSOL multiphysics software. So where this is basically a conjugate heat transfer. So the and water cooling is there. So that I have also simulated the water cooling and the turbulent
1 minute
motion.
left.
Yes, turbulent motion of has been considered. So for different LPMs, for different LPM liter per second, I have simulated. So as you can see that this is the temperature profile. So the temperature at the tungsten target is below 547 K. And the main thing is that the target should not exceed in
So
copper.
time over, please.
Yeah, it should not exceed
Now it is
390.
question answer.
Okay, fine.
I'll just ask one question only.
Yeah.
This X band target and S band target, what is the difference?
X band target and
S band Linux targets.
the target design, overall target design will not be different.
In terms of the power, can you tell?
Power is less for the X band compared to S band, but the power density is more for S band. So for that, that's why the simulation, thermal simulation was important for X band, since the power density is more.
I'm asking what are these parameters you will control if power increases in the
So we
target
can
fabrication?
increase the that water LPM that we can change, the liter per second. The flow rate we can change for more efficient heat removal.
Okay, there's one question. The heat transfer depends on flow rate or velocity?
The heat transfer, the flow rate, again the velocity of the water.
Which one is important? Flow rate or the velocity?
Both. I mean, I think the velocity is important because it has to be turbulent flow for efficient heat removal.
Okay,
Am I
time
not-
over. Thank you.
Okay, thank you.
Our next presenter is Kripa Mehta. Paper ID 1072.
हाँ
So your time is 3 minutes.
पेपर आईडी
Paper ID 1072.
Okay.
Time starts now.
Okay. Good afternoon, everybody, and let me thank the organizer for giving us the opportunity to report the performance of the 1.5 meter dia scattering chamber, which is installed at Electron Linux facility at TFR. And so this is the picture of the chamber. As our director has already mentioned, the use of such chambers in nuclear physics experiment, because we detect charge particle, and so they have to be detected in vacuum. And also the target has to be housed in inside vacuum. So the next. Okay, so this is the mechanical specification. The height of the chamber is 50 centimeter, and the wall thickness is 8 millimeter. And apart from the entry and exit port to connect to the beamline and the beam dump, there are 10 ports for various uses, like for gas feed through, signal feed throughs, and vacuum measurement, etc. And you can see that the lead is very heavy. So there is a hydraulic pump to lift it and to remove from the top of the chamber, so that we can have access during the setup. And for acquiring signal, we have high density signal feed throughs, so that we can do like complicated experiments with having more than 500 signals. Next. And this is the inside view of the chamber, where we have the two detector arms with elevated platforms. You can see there are radial holes. In the bigger one, we have 9 holes, 10 degree apart, each hole lines. So it covers 80 degree, and the smaller arm is having 40 degree coverage with 5 radial holes, where we can put our detectors at different angles and distances.
1 minute, please.
Yeah, okay. And the rotation of the arms as well as the ladder is controlled by a PLC controlled servo motors. And there are, like, it is used by the various users. We are not very familiar with the setup. So there are, we have a lot of safety things we have implemented, like hardware and software control limits have been implemented. And for the vacuum, we have two Pfeiffer turbo pumps with 1250 liters per second capacity, backed by like two rotary pump for vacuuming and roughing. And ferro seals are used for the leak-free movement of the arms. So with that, I'll conclude that this only there are a few occasions there were, like particularly with the target ladder lifting arrangement, it is done through the like screw jack
So
arrangement.
time over. Any questions, please?
Okay.
Yeah, which is the ferrofluid you have used?
Which type means it is actually we got it from Hind Highback. They don't they have not given the specification from which company they have got it.
So any development in, you are trying to develop it indigenous, this is important.
No, I did not get you.
Moving assemblies inside vacuum.
Yes.
These are the dynamic seals basically. You are trying to develop this in India?
Oh no, we are experimentalists, so we are kind of user for this.
Okay.
And, yeah, so we try to optimize the breakage in beam time and all those things.
Okay, thank you. So time is over now.
Good afternoon, everyone. I thank Good afternoon, everyone. I thank organizers for giving this opportunity me to present my work here. My presentation will be on design and development of synchronized trigger generator for 10 MeV 5 kW horizontal RF linac, which is being developed at Electron Beam Center, Kharghar. Next. This RF linac requires 4 number of synchronized triggers for its operation. One is for klystron modulator, other is for secondary is for E-gun modulator, third is for RF driver, and fourth one is for data acquisition system. So this system has been designed to generate these 4 synchronized pulses having the features of PRF generation from 1 to 400 PPS, which can be set from a remote HMI, and these pulses will have a programmable pulse width and delays. They can be adjusted online. For generating this, we have used a TI Make 320F28379 dual CPU processor. So in this figure 1, we can see here, we have to generate the four pulses. First one is a PRF, which is a reference. Second is for E-gun trigger. Third one is for klystron trigger. Fourth one is for RF driver, and the fourth one is for sample and hold. So the first E-gun trigger is a reference. With respect to that, we have to generate klystron, RF driver, and sample and hold. So we have to set the delays also from remote HMI. In second, back slide. In figure 2, we can see the block diagram of trigger generator unit. In this, we have one microprocessor card which has which uses two 32-bit CPUs, and this trigger unit accepts fast interlocks in the form of optical inputs, and it generates 4 synchronized triggers in the form of optical. To connect these triggers in the field, we have one optical to electrical conversion board, which is installed in the field only. And for RTU Modbus communication, we have ADAM module. By using that, this unit can be connected to the remote HMI. Next. So this figure 3A shows the implementation of this trigger unit. Here we can see the green color PCB which houses a microcontroller board, and remaining are the power supplies and communication modules.
Okay, so time over, please. Any questions from audience side?
Umakant, just want to know, this correction is online or it's offline?
Yes,
in the trigger pulses. Suppose you are taking reference of this E-gun. So
sir,
online, suppose there is some changes, it will get corrected automatically.
Yes, sir. It can be a program. It is programmable online also. During operation also, you can adjust the delays and pulse width during next.
No, I'm telling once you set, suppose there is some variation on the gun, Because you are taking that as a reference. Accordingly, other things will get corrected.
Sir, yes, sir. It will be the other things will get corrected online itself. The first one is a
Time over, please. Now our next presenter is Mr. Sukant Kumar Misra. 10556 per ID.
Am I audible to you?
You can connect.
No, audible है थोड़ा सा.
Hello.
Hello,
Am I,
Mr. Sukant.
am I audible?
Can you hear me?
Please increase your sound level a bit.
So, am I audible?
Feebly. Your
Yeah,
voice is very feeble.
slightly more.
So, very good.
Hello.
Hello. Can I start now?
Yes.
Good afternoon to all. Myself Sukanta Kumar Mishra, working in Pulse Power and Electromagnet Division, DRC Visakhapatnam. Today I am going to present the in-house development of linear transport driver, that is LTD, and its electrostatic parameter selection. LTD is used to generate gigawatt pulse power for radiography.
The sound.
We are not able to hear.
Now audible, sir?
Yeah.
LTD is used for the generate gigawatt range of pulse power for radiographic applications.
You have 3 minutes now. Please start.
Okay, sir. An LTD module consists of an array of cavities connected in series for voltage addition, and each cavity consists of multiple units called bricks connected in a circular fashion, and all are in parallel for current addition. Single brick consists of two capacitors charged to plus V and minus V, and spark gap switch holding plus 2V potential difference, and magnetic core that is common to all the bricks in the cavity. The brick defines the rise time, current, and period of the cavity, and hence there is no need of any bulky, voluminous oil or water tanks for multiple stages of pulse forming line, as it required the conventional mass generator to generate that kind of power for the pulse compression. It is proposed to develop in-house 3 MB 100 kA 60 nanosecond LTD module for flash radiography application to reduce the cavity size and to incorporate magnetic insulation transmission line concept. A 500 kV 100 kA 60 nanosecond LTD module is proposed here. Later on, such 500 kV LTD module will be cascaded to generate the required 3 MB voltage. So it is proposed to have developed the system in 3 stages: LTD1, LTD2.
Yes.
Please. Next slide, please. Second slide, please. Second slide. This represents the in-house developed LTD1 and LTD2. LTD1 has single open air cavity and having 10 bricks. The cavity is developed to understand the LTD concept and develop trigger source to synchronize the multiple spark gap switches. At plus or minus 30 kV, we get 34 kV output voltage, 31 kA output current, and rise time of 14 nanosecond with the LTD1. Later on, we developed LTD2, which consists of three modules of same of LTD1 and consists of 30 bricks. This is developed to generate 300 kV, 100 kA, and 60 nanosecond pulse width. It is developed to understand the voltage.
1 minute left.
Yes, sir. Voltage addition, because there are three stages are there. So by charging plus or minus 30 kV, we have get 70 kV output voltage across match load. So next slide, please. Next slide. The main parameter of the LTD are capacitors, switches, and cores. So capacitors are selected as per the output of single cavity, that is 100 kV, critical match load 1 ohm, and pulse width of 60 nanosecond. Capacitor calculated as 12 nanofarad and will be charged to plus or minus 90 kV. Capacitor dimension are 350 mm length, 150 mm width, and 40 mm height. It is considered according to the voltage crossover and compactness of the cavity. Iron-based amorphous alloy is used for the core, and core area calculated is 537 mm OD, 369 mm ID, and 45 mm height from the voltage time multiplication. And,
so thank you. Time
three
is over. Now,
Sukant, I have one question.
Any questions?
This, why in LTD 2 waveform ringing is there? one in web form 1 it is very clear, second mein ringing hai.
Actually, sir, first of all, it is not charged to that required voltage. It is designed for plus or minus 100 kV, but because this is complete system will be inside a pressure chamber, but pressure chamber is in fabrication state, so we charged at plus or minus 30 kV. So the load also not in the matched condition. So little bit of underdamped condition was there. That's why some ringing was.
I'm not asking 100. I'm asking in between there is some the ringing. Web form is not clear in that.
Second slide, please.
Some ringing is sent.
Second slide,
But it
please.
is not due
Actually,
to impedance matching, I guess.
Actually, sir, it is due to that because it is not charged to the fully voltage. Some synchronization is not possible between the all 30 spark gap switches. So
Okay,
that
okay.
Okay, so thank you, Mr. Sukanta. Now our next speaker is Mr. B. Gauri Shankar, paper ID 1058.
058, no?
Hello.
Yeah,
Am I audible?
yeah. Yes. So,
Slides, please.
PPT just we are projecting. Yes, so
Actually,
you can start now. 3 minutes for presentation. Start
Good
now.
afternoon to all. Actually, it is in continuation with Sri Sukant Kumar Mishra regarding the linear transformer driver. So I am presenting vacuum system for linear transformer driver 2. Myself and colleagues from PPMD have contributed in this work. This introduction is already over since LTD is explained by Sri Sukant Kumar Mishra. So I will explain the vacuum part. As you know, it is developed in 3 stages. One is prototype, second is 300 kV 100 kiloampere, and third is 3 megavolt. So the basic thing what we have done in the design is we have made it as modular in construction, so that we can continue to add different stages to make the system, whether it is LTD2 or LTD3. So each cavity will contribute to 100 kiloampere, 100 kiloampere and 100 kilovolt. By adding the different cavities, we can increase the voltage accordingly. Though it is different from other regular routine works because it has 3 different stages. For example, if I explain LTD2, inner part is vacuum, and again there is electrical assembly, and outside is pressure. Everything is repetitive here, but you can see in the slide 2. Please enter second slide, third slide, please. In slide 2, you can see 2 different construction. One is the single cavity in a single cavity, which you can test leak test and vacuum test. So a cavity consists of
1 minute left.
Two SS chambers with acrylic sheet in between. So you can test with the acrylic sheet or without acrylic sheet. So it can be very easy during the manufacturing or even testing. In the third last slide, we can see it is completely assembled. One single cavity we are leak testing here, and 3 cavities we are leak testing here. So we have leak tested the system into 1 into 10 power minus 9 millibar liter per second. We have tested at individual stages, and on the final stage also. Now the pressure chamber is also arrived. Because it is different from other, we have used 2 o-rings radially, one inside and one outside.
Okay,
to
time
take
over,
care
please.
of.
Any questions, please? Question to audience. Yes, please. Any online questions? So thank you very much. Now our next presenter is Mr. Surendra Kenikela, paper ID 1065.
Hello.
Hello.
Hello, am I audible, sir?
Mr. Surendra.
Yes, sir.
Yeah, can you hear me?
Okay. Yeah, yes. Sir, is it visible, sir? Visible my screen?
Your sound is slightly not audible.
Yeah.
Hello.
Hello, sir.
Mr. Surendra. Hello.
Yes, sir. Hello. Hello, is it audible, sir?
Sound is very low. Can you Increase the volume.
Yes, yes, I increase. Sir, is it right now okay, sir?
Hello.
Hello. Sir, is it right now okay, sir?
Okay, I think
speak
you can
loudly.
start. Yes, please speak loudly, and your time starts now. 3 minutes, please.
Okay, okay, sir. Good afternoon, respected sirs. My name is Surendra from Andhra University, Visakhapatnam. Present, my topic is effect of rare earth elements on absorption or aspects of titanium, cobalt, rare earth included, and zirconium, cobalt, rare earth included. Next slide. So now we are using titanium and zirconium are in non-evaporable getter materials widely using right now. So I am taking that here in this work. I am presenting some samarium and gadolinium, mixing that what the impact of showing of the NEG materials. So my material is taken and preparation of my material and so on. I am preparing that finally make a and pellets like this. You're showing the fourth figure. So I'm not prepared that one is that samples are taken centered 1000 degrees centigrade, and now after that I done an analysis. Next slide, sir. Here I'm doing high temperature XRD analysis. High temperature is a phase change for transformation, phase changing identification. Then second one is what is that? So thermogravity analysis slide. This is the most important topic of the part of this in this study. So we are observing absorption of the residual gases in this given. So we are observing 400. So before previous studies, titanium cobalt or zirconium cobalt, they are taken from 600 around 700. They are absorbing
1 minute left, please.
Okay, sir. Now in this study, we are observing from 400 and 500 observing capacity is increasing while you are studying this. Next slide. So finally, we are doing this one. XPS also do analysis. Thank you, sir.
Okay, so any questions, please?
Yeah, Surendra, do you carry out certain recharging of this energy? Is it possible to recharge them after some time?
Yes. We are trying to trying to do this analysis. Now we are doing just trying to doing. Some analysis are done. Some analysis are still going, sir.
Okay.
Okay, thank you, Mr. Surendra.
Yes,
Now let us move on to paper ID 1067. Is Sukriti Hans. Hello. Hello, Miss Sukriti Hans. Can you hear me? Hello. Okay, so now, can you hear me? Hello. Hello, Miss Sukriti Hans. Can you hear me? Okay, so now let us move on to next.
And you can take it again.
Yeah.
Try to.
After some time we will try. So now next speaker is 1068 paper ID. Sudarshan Jibu Bhai Wala.
Yes, sir. अच्छा, उनको बाहर से कॉल करवा देता हूँ किसी से. You will take it up. We'll try it.
Can you hear me?
Yes, sir.
Okay, so your time starts now. 3 minutes.
I have to say.
We are streaming the paper.
So good afternoon all.
My presentation on the development of the 2.45 gigahertz ECR ion source for the spacecraft plasma interaction experiment. Next slide. Yeah. So this is the fixed machine. So in this fixed machine, we are simulating the low Earth orbit plasma environment at the in the ground. Basically, it's a 1 by 1 meter vacuum vessel. Okay, so here we are replacing the foreign made ion source with our local made ECR ion source. Okay.
Sound, can you slightly louder? Can you?
Now it's okay.
Yeah, you are
Yeah,
audible.
So you can see that this is the experimental setup. So the one end is connected with the vacuum system. This is the diffusion pump and the rotary pump kind of a vacuum system. And in the one port, we are inserting the Langmuir probe to measure the plasma density and temperature. In the one port, we are putting our indigenously made ECR ion source. Okay, next slide. Yeah. So this is the 2.45 gigahertz ECR ion source we have developed in IPR. So in the first figure, you see the basic component of the ECR ion source. So here we are using the NdFeB permanent magnet to produce the magnetic field. These all are magnetic field in the exact direction, and we are using this magnetron-based microwave source. Oh, so in the fourth figure, you see the magnetic field measurement, and this is the photograph of the SPIX experimental setup. Okay, so this setup we require the plasma density in order of 10 to the power 12 per meter cube, and the plasma temperature is around 1 to 10 eV. Okay, basically this ECR ion source produce the high density plasma, but this vacuum, the vacuum.
1 minute left.
The vacuum vessel is very big, so we can use this advantage of the pressure gradient. So we produce the small plasma, high density plasma, and propagate into the vacuum chamber, and we get the desired density. Next slide. Next slide.
Next slide.
Yeah, so this is this slide here shows the result and summary. Here you can see the photograph of the argon plasma. So we have measured this low density plasma and temperature with the detachable spherical 1-inch diameter Langmuir probe. So we have successfully made this indigenously made this 2.45 gigahertz ECR ion source under the Make in India project, and we have replaced with the foreign one. And we achieved the plasma density in order of 9.8 10 to the power 11 to 5.8 10 to the power 12 as a function of the various microwave power, and the plasma temperature is in the range of 3.7 to 5. Okay. Thank you. Sir, you are.
Now time is over.
Yeah.
Now any questions, please, from audience side?
Yeah, Sudhir Singhwala,
Yes,
this magnetic field you have put in the ECR ion source, what is the shape? Is it generating a solenoidal field or multipolar field?
So it is, sir, we are using this NdFeB permanent magnet. All the three ring in the axial direction. So we are producing we are basically interested to produce the volume plasma. The magnetic field is a flat.
It's flat. Okay, so you want to put the
magnetic
magnets.
mirror kind of thing.
Yeah, you want to put the magnets inside vacuum, or they now they are outside vacuum?
It is outside the vacuum.
Okay, you don't want to put them inside to generate higher fields, but
No, sir. So because we need only 875 watts for the resonance for 2.45 gigahertz.
Okay, for which particle? This ion source is for which particle?
So we have produced here argon plasma. Also, we are producing the deuterium plasma, and we expect deuterium beam for the other experiment also.
Okay.
Okay, thank you.
Thank you, sir.
Now our next participant is Shreya. Again, paper ID 1073. Okay, so your time starts now. 3 minutes.
Good afternoon once again. So now I will be presenting my work on electron optic simulation of 40 kV bombardment type solid cathode electron gun. So I'll want to go to the next slide. So this is the electron gun geometry and these are the parameters that we want to achieve. The beam voltage is 46 kV and the beam current is 100 milliampere. So now for this gun we have a cathode which is a solid tungsten cathode. Now we have a filament which is sitting beside this tungsten, and so we are heating. So it is an indirect heated type of cathode, plus there is an electron bombardment also. For that also the tungsten temperature is increasing. So as you can see from the image that it has a focusing electrode. It's a diode geometry with a focusing electrode and Pierce type of gun geometry. Next slide. So this is the simulation result. Now this will be operated at in temperature limited region. So as you can see that if we generate the electron beam trajectory in space charge limited operation, the current is around 5 ampere and also the beam size is more. So we need to operate it at temperature limited region. So the aim of this simulation was to find out the temperature which where we can get the our required amount of beam current. So this is the trajectory when the temperature, cathode temperature is around 2300 K, and this is the beam size at the anode exit, which is around 2 mm. Next slide. So
1 minute left.
yeah, so I'll come to the last slide where I have generated this beam current graph as a function of cathode temperature. So from this graph we can actually find out that at what temperature we would like to operate the gun to extract the desired beam current, and also the beam size. As you can see that beam size doesn't change when the temperature of the cathode is changing from 2200 to 2400 Kelvin. So that's it.
Okay, thank you. So now it is time to question answers from audience, please.
Yeah. Share you are going for temperature limited gun.
Yeah.
I think for better properties of both beam size as well as achieving the convergence of the beam. Can you achieve the same thing with the design of electrodes?
Design of electrode. So you want to
In
say
the
that
space.
in space charge limited. Yeah, that will be ideal. But this here what was we were given the profile, the beam electrode profile. So here our aim was to find out the properties. I mean how to the properties of the cathode temperature, but we can improve on the design. And as you have mentioned that space charge limited region operation is much better compared to the temperature limited operation.
Okay, thank you, Shreya. It is time is over. So now, Sukriti, can you please unmute? Can you hear me? Sukriti Hans. Sukriti Hans. Hello, can you hear me? Miss Sukriti Hans, can you hear me?
He's saying yes, but we are not able to hear.
Just speak.
Hello. So
We send a request also.
unable to
Can no, we cannot. We can send a request.
He's not able to unmute her.
you ask him mute, unmute, mute once or twice, then she can do.
No.
This is the only way. There are no hardware ports.
What is sending a request?
poster also.
Okay, so 1076. So now, sorry, we could not make proper contact with Sukriti. She is not audible here. So now next is 1076. Mr. Satyendra Kumar. If he is there, he can come. ठीक है, next. Satyendra.
कैमरा 70 days ना?
76.
आपका हो गया?
6 years. आ गया?
Devranjan Das has given message.
Okay, so now you can start. 3 minutes time is there.
Yeah, good afternoon all. Yeah, the presentation is regarding the experimental study of parameters which are affecting the waviness in electromagnetic welding. As lot has been talked about electromagnetic welding by Sri M.R. Kulkarni. So I will skip the introductory talks. Please skip. Next. That's all. So this is for this purpose, the study which has been undertaken is the welding of D9 tube, which is a clad over tapered SS316LN plug. So this is the geometry shown for D9 tube. Over that yellow color is the copper driver, and that below that it is the SS316LN plug. So these are the dimensions of D9 tube. 21.4 mm is the OD, 0.7 mm is the thickness, and we can see that there is a tapering on the SS316LN plug. For electromagnetically welding the D9 tube over SS316LN plug, we need to pump the current in an electromagnetic coil, and this is the typical current signature, and the figure shows the photograph of electromagnetic coil. Next, please. So this is the welded sample. We can see that ablated copper driver over the D9 tube, and below one is the cut section of copper D9 tube and SS316LN plug. So for one-to-one comparison of the parameters which are affecting the waviness, a fixed point has been taken to study all the parameters, which is 7 mm from the right side of the tube, and the length of that region is 250 micron. So there are 4 parameters which affect the waviness. There are bank energy, taper angle of the plug, standoff distance between plug and tube, and the frequency of current pulse. Next. So first parameter, which is the bank energy, we have used 100 kilojoule bank, which have 64 microfarad of the capacitance. And the charging voltage starts from the 17 kV and it goes up to 19.5 kV. Corresponding to 17 kV, we have the energy 9.25 kilojoule, and we have pumped energy from 9.25 kilojoule till 12.17 kilojoule. So we can see that at 9.25 kilojoule, there is hardly any waviness, but it is a metallurgical weld because it passed the leak test and everything. Also, we can see that it is a wavelength as well as crest height both increases. Next, please. This is the taper angle. We can see as we increase the taper angle of the plug, wavelength as well as crest height increases up to a certain point. Afterward, it starts reducing. Next point. Next, please. Next, please. Yeah, and same behavior is seen in the standoff distance. Up to a certain standoff distance, which is 1 mm, we can see that there is an increase in wavelength as well as the crest height in the waviness. Next point. Next slide, please. And this one is the behavior as seen by changing the frequency of current pulse. It's a continuous increase in the waviness parameters, which is the crest height as well as wavelength. And we can see that on increasing frequency and bank energy, there is a gradual increase in the
Now, audience, please, any questions?
Okay.
Yes,
Which
sir.
parameters will change? The material of the flat material change. Say material of low conductivity.
Sir, we are using a copper driver. So conductivity, if the low conductivity material, then copper driver will take care of that. So if the hardness is more, say yield strength is more, we need to pump more current, which is we need to charge bank to a certain more voltage, sir.
Okay.
This will. So now next speaker is
Thank you, sir.
Mr. Deeptimai Viswal. Deeptimai, can you hear?
Yes, sir.
Yeah. So paper ID is 1077. So you can start now. Time is 3 minutes.
Good afternoon, everyone. Today I am going to present on characterization of atomic vapor source for ytterbium by mass spectroscopy detection in QMS. Most often time, environmental sample is available in aqueous nitrate form. So for trace level spectroscopy using resonance ionization mass spectroscopy requires that species should be available in atomic form. So we have developed a atomic vapor source to generate atoms from aqueous nitrate solution. So here I am going to present our work on generation of ytterbium from YbNO3 solution. So the concept is that on at higher temperature, Yb nitrate decomposes to yield ytterbium oxide Yb2O3, and using a suitable reducing agent, that Yb2O3 reduces to Yb atoms. Next slide, please. So experimental setup consists of atomic vapor source and one quadruple mass analyzer system. The atomic vapor source is consist of graphite crucible, which is held by two water-cooled copper electrode, and it is resistively heated. So the sample present in the graphite crucible gets heat and volatile the atoms. The thermal characteristic of the atomic vapor source I have shown here. That source can go up to 2200 degrees Celsius. Actually, I am using a pyrometer with range 550 to 2500 degrees Celsius.
So 1 minute left, please.
Yes, I cannot measure below 500 degrees Celsius. So my data I have shown in current. Next slide, please. So here what happened at lower temperature below 200 degrees Celsius, Yb nitrate first dehydrates to form ytterbium nitrate, and when the temperature rises beyond 250 degrees Celsius, then Yb nitrate decomposes to Yb2O3, and that can be seen by the mass spectra when it is 0 ampere. Only the background it is only high, means the water vapor and argon. I used argon to vent our system, so it is only argon mass spectra. Then when I increase the temperature, the mass spectra around 18 AMU it increases, and at 10 ampere it is maximum. Then beyond that, the mass spectra around 18 AMU it is reduced. That means the dehydration is complete. Then beyond that means when I increase the current, then nitrate decomposition of nitrate starts, showing the mass spectra of nitrogen and nitrous oxide and nitric oxide shown in the mass spectra.
Your time is over. Please now any questions from audience side? Okay, so there are no questions. So thank you, Deeptimai. Now our next presenter is Mr. R.V. Chavan. Paper ID 1078. Yes, your time starts now. 3 minutes, please.
And these electrons then for the filament everything is a 5 electrons. And then for the process, the thing for the vacuum. System requirements are to automate the filament conditioning process, GUI to display all the required parameters, provision to for user-defined vacuum till limits, and voltage ramp-up time, database to store the parameters. Next, please. Feature of the filament power supply is it is the motorized variac with the specialized gear assembly to reduce the speed, local remote operation, zero start to avoid the thermal shock. In case of any external fault, it will reduce to the 0, and output voltage and current are available in the form of 0 to 10 volt for DC monitoring. The schematic is given. In this, the embedded controller is used, and the I/O are connected to the filament power supply. And through the vacuum gauge, we are reading the vacuum, and as per the vacuum in the
Now 1
gauge,
minute left.
we decide the conditioning. Next, please. This is the GUI from where the user can put the trip limits, vacuum limits, and ramp up time. Next, please. So the software implementation, the user can define the ramp up time in how much time it has to rise, and vacuum trip limits are the conditioning should start with the 1 into 10 to minus 7 millibar. If the vacuum layer degrades the 5 into 10 to minus 6, the ramp up procedure will wait for more time. If vacuum further decreases, it will reduce the voltage, and if vacuum degrades below minus 5, it will reduce it to 0. Next, please.
Okay, time over, please.
Conclusion.
So now any questions from audience side?
Johan, can we use solid state devices in place of demestat like inverter or something like that?
Actually, the gun is floating
SMPS,
at 50
SMPS.
kV. Sorry, sir. The gun is floating at 50 kV. So we need some isolation between the filament power supply and the electron gun. So here we use AC transformer, step down transformer, and it got the isolation of 70 kV. So in solid state, it will be difficult.
Okay, so thank you. Now another paper is 1080 paper ID, Mr. Chavan. So we will continue with that.
Yes, sir. So my next paper is design of control for electron beam characterization. Next, please. So the electron gun are used for as an injector in the accelerator, hence the beam quality plays vital role. To assess the beam quality, we are doing the characterization. In beam characterization, the size of the beam is measured at the various distance and various angles from the cathode. To do that, we need the control system with proper instrumentation. Next, please. The system requirement are to measure the beam size of 3 mm to 10 mm, a embedded controller, a motorized precision Z-shift linear encoder with the control unit to move the linear in microns steps, sample and hold to measure the pulsed electron beam because we are characterizing the pulsed electron beam, and database to show the beam characterization data. Next, please. So major components are electron gun, of whose the beam dia size is going to be measured, and the gun monitor which generates the 50 kV pulse to extract the beam from the electron gun, the embedded controller to generate the pulses for sample and hold and the gun modulator, motorized control precision Z shift which moves the slit inside and out to in the micron level steps, and sample and hold circuit.
1 minute left, please.
Sample and hold circuit to measure the measure the pulse signal which are in the order of 10 to 15 microsecond. Next, please. So this is concept is we are using the 09022 embedded controller with 8 loss chassis which has got FPGA which generate the pulses. The pulses are generated by 9401 TTL generation. Analog input module is 9201. The motorized control precision linear Z is controlled over RS-232 protocol, and computer is required for GU and to store the database.
Okay, so time
So
over.
this is the unit.
Now any question answers, please.
Then I'll ask one question.
Yes, sir.
This embedded controller you are using,
Yes,
so
sir.
what sort of isolation between the high voltage side, I mean, it may be 230 volts only, and on the control side?
Yes, sir. For digital signal, we are using the relay, which give the physical isolation, whereas for analog signals, we are using the analog isolators, which give the insulation of up to 3 kV.
Okay.
Okay, so thank you, Mr. Ramchandra Jawan.
Thank you.
Now, Our next speaker is Mr. Abhijit Tillu, paper ID 1079. Mr. Tillu, can you hear me?
Very clear.
Yes, so please start.
1079, sorry.
So this talk is on the protection mechanisms that are used for the high power pulse magnetrons. So there are two issues in when we handle such tubes. One is the filament and other is the arcing. Next slide, please. So when we are doing these things, we have to take care of, as I said, the electrical arcing that is taking place in the high voltage part of the magnetron. Now these magnetrons are prone to routine arcing even after they are conditioned. So the manufacturer, I have taken a typical example of a M5028 tube, which is being used in our cargo scanner project. This magnetron, the manufacturer is allowing 25 consecutive arcs. And if there is excessive arcing, then there is a irreversible damage that is happening to the tube. For that, we have implemented a arc counting mechanism. Next slide, please. Next. क्या हो गया?
इसी क्रैश हो गया।
अच्छा, ठीक है, मैं बताते जाता हूँ। तो इसमें क्या है कि आर्क काउंटिंग मैकेनिज्म में क्या है कि वी आर काउंटिंग कॉन्सिक्यूटिव आर्क्स।
इधर से ऑन
तो इसमें क्या है कि अगर मतलब 20 हमने वी आर अलाउिंग 2 आर्क, 4 आर्क, 8 आर्क एंड 16 आर्क। तो अगर आफ्टर इफ यू हैव पुट अ सेट पॉइंट ऑफ 16 आर्क्स और अगर 8 कॉन्सिक्यूटिव आर्किंग के बाद में एक क्लीन पल्स आया तो भी नाउ द आर्क शुड स्टार्ट काउंटिंग अगेन. So that mechanism we have implemented with normal digital TTL controls as well as with DSP.
Okay, 1 minute left.
Secondly, for filament soft start, along with filament soft start, magnetron is a very funny device. The more the output power the more the power that is injected into the magnetron, the more the heating that takes place on the cathode. So the cathode temperature has to be reduced. So the manufacturer gives a chart कि इतना average power है आपका तो cathode temperature ये होना चाहिए. So according to that chart, we are controlling the filament power that is going into the magnetron. So for that, we have used a very innovative method of measuring the pulse current, averaging it, and after averaging it, that average value is correlated with the power that is going into the magnetron. And that correlated value is finally fed to the PLC for deciding on the average filament power. Next slide, please. Next slide. So in conclusion, I would say that this scheme has been tested, verified, and 3 such modulators are operational at EBC, out of which one is being used in dual energy accelerator, and there is no problem.
Thank you, Mr. Tillu. Now time is over. Now any questions from audience side?
Yeah, how do you detect the arc?
So this is a standard line type modulator. In case of arcing, the load impedance changes drastically, reduces drastically, causing a negative mismatch on the impedance line, on the pulse forming line. And that current is routed through a different resistor divider combination. So we are sensing the arc by putting a CT across that.
Okay, now CT measures pulse current.
We are doing a galvanically isolated ferrite based CT for that.
Okay. Okay, thank you.
नहीं है.
क्या मैंने किया क्या?
1081.
म्यूट
Okay, so your time starts now. 3 minutes, please.
Yeah. Thank you for the opportunity to speak here. I'll be talking about radioactive ion extraction and transport system. And so the radioactive ions are very useful, and then it has been discussed by many people in this one, like specifically that Dr. Krishna Gopal has introduced certain aspects of this one in the introductory talk. And even they talked about the whatever the high current electron and LINAC accelerator, which is coming up later in Vstaa kind of thing. So actually that made my talk more easier. So we need the radioactive ions for studying exotic nuclear properties like halo structure, Borromean structure, and things like that. And they also have applications in super heavy element production and nuclear medicine command, etc. And so without going too much into detail, so the idea here is to use the electron and proton accelerators, and then from electron you convert into photon by converter target, and proton directly will be hitting a target, actinide target. So actinide targets go through a nuclear fission reaction, and then at lower energy they actually produce a lot of neutron-rich exotic nuclei, which are very much required for our studies. So that is the basic thing. So next slide, please. Yeah, so now the challenge is actually like having huge current and having actinide target. There is a lot of fission fragments and all these active things are produced. So how do we extract? Because we need a large effective thickness of the target to have large yield. That
1 minute left, please.
Yeah. So for that there are two methods: diffusion efficient and gas jet method. And so both the methods we are proposing to utilize. Next slide, please. So you can see the one of the schematics of the proposal here, and so there is a chamber here, and where we can mount the target, and then we can get it irradiated. And some in gas jet method, the gas is flown and through this one, and then the gas is actually taking away the radioactive elements to the skimmer system, which is pumped by roots pump and things like that. And then the radioactive element are stopped in the catcher file, and by counting we'll get to know the efficiency and things like that. So this is actually a pre-project kind of activity where we want to have the efficiency of the extraction and things like that. Next slide, please. Yeah, so with this method, we will be using the existing target making facilities at BRC, and then we will be radiating the targets at accelerator facilities at Mumbai. And we will apply these two methods, and then we will be using gamma counting techniques to extract the efficiency of for the transport and things like that. Thank you.
Okay, so time over. Now, any questions from audience or online? Okay, so no questions. Then thank you, Mr. Ramchandran.
Welcome.
Now our next speaker is Ramesh Chandra Das. Paper ID 1082.
PDF.
8 to 10 पेपर बचे हैं अभी
वही 8 to 10 जो बताया सर।
तक खत्म करना
Folder. Now could we get?
Share is opening.
आधा घंटा में
ठीक है, 15-21 से 16 मिनट तक ये समय दिया गया। 39 मिनट्स में 7 पेपर।
टाइम बहुत
बेचारा शुरू करता है तो शुरू करता है नहीं, पोस्टर जब हार्ड कॉपी रहता है ना तो काफी इंटरेक्शन का चांस रहता है। करना
क्वेश्चन है भी तो एक ही क्वेश्चन पूछ सकते हैं। Okay, so
पीडीएफ नहीं कर सकते।
Okay, so please start. Your time is 3 minutes from now.
इसमें डिफिकल्टी हो रहा है पर
हो गया
फुल स्क्रीन नहीं दिख नहीं रहा है।
एक काम कर सकते हैं, प्रिंट आउट भी दे दो।
प्रिंट आउट का
ठीक है इसी मोड में चल रहे हैं।
Good afternoon. My title is the time of flight mass spectrometer based RIM setup and some applications. Next. Next नहीं आएगा।
So our next speaker is Rohit Shukla, paper ID 1083. Mr. Rohit, can you hear? तो शुक्ला जी से भी कांटेक्ट नहीं हो पा रहा है। तो अगर
आपको summarize अभी का भी करते हैं.
So our next presenter is Udayagiri P. Singh Sachan. Paper ID 1084. हाँ ये तो इधर ही है ना. So we can start ना. Okay. So please start.
सर स्लाइड्स शेयर नहीं हो रही है.
स्लाइड्स भी इसमें करो एक जस्ट एक
1084.
हाँ
PPT ले लो. नहीं तुझे कितना देना है? देखना फुल लोड हो गया. हाँ
सर 1084.
84.
तो बंद नहीं होता है.
Okay, so your time starts now. 3 minutes, please.
Okay, so good afternoon, everyone. Myself Udayagiri, and I am going to present design, development, and commissioning of 3.65 Tesla superconducting magnet for high gradient magnetic separation. Next slide, please. So in this slide, we will discuss what is high gradient magnetic separation. This magnetic separation technique, it is a unique technique which allows materials with different magnetic properties to be separated by using inhomogeneous magnetic fields. So due to the advent of the superconducting magnet technology, we can produce high magnetic fields, due to which the weakly magnetized particle, such as paramagnetic particles, they can also be separated with the help of this technique. So this HGMS technique, it finds application in the mineral industry, manufacturing, nuclear, as well as in medicine and environmental technology. On the left hand side, I have shown a schematic that how does this HGMS process takes place. First of all, we will put the feed in the suspension, in which the feed will consist of the particle which are somewhat slightly magnetic in nature. Now there is a magnet, so the magnetic field will be in the axial direction, and the feed flow direction should be in parallel to the magnetic field direction. In this central pipe, we have filled a ferromagnetic material. In our case, we have put a ferromagnetic wool, SS430 wool. So what happens, due to this magnetic field is produced, and due to this ferromagnetic wool, gradients are produced near to the wire surfaces. Now what happens, the particles, आवाज नहीं आ रहा? नहीं. The particles, they get stuck on this mesh, and after the separation process, the field is closed and the particles are separated. Next slide, please. So here on the right hand side, I have shown the process. On the top of the circular portion, it is showing the ferromagnetic wire. On the top, which has been shown by the black colors, there the diamagnetic particles will settle down, and on the y-axis, the paramagnetic particles can settle. So
1 minute left, please.
okay, so the forces are like the magnetic force. It depends on the susceptibility, magnetic flux density, and the gradient of B. So the SS wool which we have used, that is producing a gradient of 10 raised to power 4 Tesla per meter. Next slide, please. So this is the superconducting magnet of 3.65 Tesla, which we have developed. Here we are using a ferromagnetic wool, which I have shown here in the figure. It has been filled in this bore pipe. Next slide, please. So this shows the test results. The magnet has been cooled to 3.1 Kelvin, and the magnet has produced a field of 4 Tesla. Our requirement was of 3.65 Tesla, and we have checked it for the higher fields also. Yeah.
I'll ask one question. So whether
Any questions from audience?
whether it is industrially it is utilized somewhere?
Yes, sir. In industry, it is used in the like metal processing industries, for the case of gold and platinum, which are very precious metals. The particles which are coming out in the tailings, they are extracted in this method.
Okay.
Okay, so thank you. Our next presenter is Mr. Sunil. Paper ID 1085. 1085.
रोहित शुक्ला का मैसेज भी हाँ वो रेडी है विशाखापट्टनम गगन
Mr. Sunil, can you hear? Sunil. Mr. Sunil Kanchi.
I'm present here. Am I audible?
Yeah. Okay. Now we are loading the paper. So please start your time. Start from now. It is 3 minutes.
Okay, sir.
Please.
Good afternoon to everyone. My presentation is on electrical circuit modeling and simulations of plasma opening switches. And opening switches are very important in conjunction with the inductive storage for development of giga and terawatt applications, which may be applications like accelerators and flash radiography and jet pins devices. And mainly inductive storage has an advantages of 10 to 100 times energy density when compared to capacitive storage devices, and for efficient transfer of energy from switch to load, the vacuum line, which is a plasma, the magnetically insulated line in a plasma opening switch chamber, must have low impedance and low inductance. And the inductance of the generator should be low, such we get high currents and high voltages in the output stage. The plasma opening switch mainly used for enhancing the voltage and power, and it is mainly the multiplication of voltage and power. The next slide, please. Here, the electrical governing opening switch mainly will be in the parallel with the load, and it has 4 phases. That is conduction phase, erosion phase, and enhanced erosion. Last phase is the magnetic insulation, where the conduction phase lasts for hundreds of nanoseconds, and it depends upon how the energy transfer mainly depends upon how much time it lasts. And mainly the opening of this plasma opening switch is governed by erosion, enhanced erosion, and magnetic insulation phases, which the screen shows the different phase governing equations. And this D is the mainly the parameter which plasma sheet thickness, which will be opening.
1 minute left, please.
Okay, sir, I will complete. And next slide, please. And these are the simulation results which we obtained with the parameters shown in the table 1. Here, this shows the current, switch current and load current waveform for a density of 1 into 10 power 14. And this is the voltage which we obtain at 1 into 10 power 14 per centimeter cube. And this is the how we modeled with the diode load model. This is the load resistance, and how the switch resistance will vary as shown in the figure 4. Next slide, please. And this is this insight gives these three figures shown in the insight gives us to how much current and voltage can be obtained with the variation of cathode radius, ion density, and ion velocity. And this for us gives a insight development for terawatt facility. And the and mainly the POS will be operated in a vacuum with a millibar, 10 power minus 4 to 10 power minus 3 bar. And thanks, this is the simulation. Thank you.
Okay.
Hello.
Sir, bol.
I would like to know this opening switch, what is the effects of the wire diameter? And if any medium is introduced, suppose gases, so how it will work?
The effect of
effects of the wire diameter and insulating medium.
Wire diameter.
Wire diameter. See, you are
This
using
is
wire for
mainly
exploding.
plasma will be injected through plasma guns. Here we won't use any wires.
You are not using exploding
No, sir.
wire?
No, sir. We use plasma. Plasma will be injected through plasma guns.
Okay, okay.
Okay, one question here.
Yes, sir.
Out of the energy storage devices between superconducting magnetic energy storage and capacitive and battery, which one will have the highest energy density per unit volume?
Sir, superconducting and superconducting will have a higher energy density.
Even battery. Can also put batteries into it.
With the battery, sir. Sir, I didn't hear.
Yeah, which has the highest energy density?
When comparison with sir, battery
all three capacitive,
density,
inductive and battery.
but the discharge time will be very high for the batteries. So we need power.
Okay, so thank you, Mr. Shukla, Mr. Kanchi. Now, our next presenter is Mr. Rohit Shukla. Paper
am I audible?
1083. Can you hear me? Mr. Rohit Shukla.
Sir, am I audible to you?
Yeah. Mr. Rohit Shukla.
Yes, sir. Yes, sir.
Yes.
From the same login of Sunil Kanchi.
Kanchi is Kanchi.
Now,
my name is Rohit Shukla, sir. I am Rohit Shukla.
Yes. So, yes. Now your time starts now. 3 minutes, please. Hello. Please start your presentation. Is there any problem?
Mute दिखा रहे. Hello.
Yeah. Yes, you are audible.
I am at present from Sunil Kanchi login. So please continue that login for 3 minutes. Okay. Okay. So, sir, in this, first of all, thanks to the Vstaa for giving us opportunity to present the plasma focus work, which is basically a very miniature and a small neutron source, which has been developed by PPMD. And the beauty of the system is that it is
किसका रोहित शुक्ला का प्रेजेंट कर रहे हैं कांची?
मैं खुद प्रेजेंट कर रहा हूँ सर. मैं रोहित शुक्ला प्रेजेंट कर रहा हूँ.
Yes. Okay, please continue.
So the plasma focus is basically a truncated coaxial gun in which very high current discharges at a very optimized gas pressures. And if they are deuterium, then the fusion-like conditions occur in the very small volume of the system. And because of that, the neutron emission takes place. So there is a well-established neutron emission yield basically reported, which is basically current raised to power 4 or 5 from the plasma focus system. So we have developed, our objective was to develop a very small and portable system with totally indigenous resources, means not very costly components. And in that sequence, we could deliver a plasma focus of nearly 10 to the power 7 neutrons per shot being emitted. And that too in very compact configuration, which I will be showing in our next slide, sir. So next slide, please. So this is the whole machine. You can see that it comes within feet of the dimension, 2 feet long and 1 feet, I think, wide. And this is the schematic diagram in which there is not very complex scheme, but the capacitor bank itself is directly connected with the plasma focus, and there are no external transmission lines connected from the coaxial external transmission lines connected, and the system is made so low inductive that the current in this small configuration are reaching nearly 170 kiloamperes of the current. And because of that, we are able to get the neutrons from this portable system. So next slide, please. Yeah, so this is the waveform. Actually, when I said that the gases are optimized, the first top waveform shows that the event, which is noticed by very small, very strong glitch in the di/dt signal, occurs at the peak of the current. Means when the current is peaking in the system, nearly 180 kiloampere current into that. At that time of
You have 1 minute now.
At the time of occurrence, the fusion reactions take place, and we have recorded PMT signal, B dot signals, and next slide, please. I will show you that the neutron signals have been consistently noticed from this machine, occurring at 10 to the power 7 neutrons per shot, and we can fire it repetitively, certainly, and every component from the system is indigenous. So this is one technological aspect, and you can have a mobile neutron source, 9.5 kV operating voltage, 10 to the power 7 neutrons consistently given. And for this category, this is the, I would say, that is smallest system developed in the laboratory. Basically. Thank you, sir. This is all.
Okay, so any questions, please?
Dr. Shukla, I have one question.
Yes, sir.
You have also worked on 9 MeV Linux for neutron generation.
Yes, sir. We are developing
the idea, na? So this how you differentiate both?
So that is continuous source basically, because that is photoneutron source and continuous are coming. And
so
here
whether this find application.
Yes, sir. This has application in diagnostic development, and for some of the basically radiation shielding testing also, we are developing this for that purpose also. And of course, ion application and other different applications in the plasma.
Thank you, Dr. Rohit Shukla. Now let us move to next speaker.
Thank you very much.
ID 1086, Mr. Anik Majumdar. So Dr. Anik Majumdar.
Am I audible?
Yes, yes.
Okay. Can you kindly share my slide?
Just it is streaming. 86.
Okay.
Yes, so you can start your presentation. You have 3 minutes from now. Please.
Okay. A very good afternoon to the judges and all the attendees. My name is Anik Majumdar, and today I am going to present on oxidation of samarium in high vacuum during laser-based isotope separation process. Our group is currently focusing on developing laser isotope separation process for samarium, ytterbium, and lutetium for medical application. Now, in this process, we evaporate the charged metal, which is the mixture of the isotopes using suitable evaporation technique, and inside a vacuum chamber. So when the metal vapor expands in vacuum isentropically, it makes a vapor jet, which then gets suitably collimated and trimmed to make a monodirectional atomic vapor beam, which is addressed by a fine-tuned laser source, and the laser, by interacting with the atom, selectively ionizes the desired isotope of concern, and those photoions are then collected using a suitable electric field. Now, we can say that a vacuum is the best barrier against the oxidation of any metal we can provide. But in our process, due to high temperature, we have seen that inside the vacuum chamber also, inside the vacuum chamber also, it gets oxidized. The next slide, please. Now, in laser isotope separation process, no, previous slide, as I was saying that even in 10 to the power minus 5 millibar, samarium reacts with the background gases and forms oxide. The oxidation rate depends on volume to surface ratio, exposure rate, temperature, etc. As our experimental temperature was somewhere around 1000 Kelvin, we first started our experiments at 673 Kelvin to 923 Kelvin, and because vacuum compatible thermogrammetric analysis was not available, we did it with flowing air and flowing argon. Next slide, please. So from the isothermal, from the isothermal thermogrammetric analysis, we can say that it is a parabolic in nature, the oxidation of samarium, which shows that it is diffusion controlled. That is, the diffusion of metal and oxygen through the oxide layer is rate controlling. Also, you can say the experimental specimen after 6 hours, and micrographic analysis also shows that the presence of oxide layer. We have also calculated the oxidation rate at different temperature and different condition. Next slide, please. And we can conclude that, next slide, yes, the apparent oxidation rate at 3 different temperatures for samarium we have calculated, and the oxidation rate varies largely with the temperature and gas flow. And the experiment in vacuum chamber was not successfully concluded because of some experimental error of the indigenously made vacuum balance. Thank you.
Okay, thank you. So now any questions from audience?
Yeah, one question only. What is the efficiency of this process?
The evaporation process there, or the whole process?
The whole process maybe.
Basically, if we evaporate, the evaporation efficiency is nearly 1%. If we evaporate 100 atoms, probably 1 atom goes to the photo interaction zone. And then the overall process efficiency depends on 2 other efficiencies, which is the photo interaction efficiency as well as the collection efficiency. So that has to take it back out.
Okay, thank you, Dr. Majumdar. So now our next speaker is Mr. Dev Ranjan Das, paper ID 1087. Loading. So Mr. Dev Ranjan Das, can you hear me?
Yeah. Very good afternoon, everyone. My name is Dev Ranjan. So Anik
Some
spoke
sound,
about
can you speak slightly loudly?
Yeah. Is it better now?
Yeah.
Yeah. Okay. So my name is
Yeah,
Dev Ranjan. So I'll be talking about the PLC-based control system for the laser isotopic separation process.
You have 3 minutes. Okay.
Yeah. So Anik spoke about the laser isotopic separation, the previous speaker. So I'll be talking about the control system for this laser isotope separation process. So as Anik was explaining the laser isotopic separation, what happens is we evaporate the charge in a crucible, either using resistive heating or electron bombardment heating, and then the vapors generated are exposed to laser radiation. Now, due to the laser interaction, so the ions are the one targeted species get ionized, and then it is extracted by applying an electric field. So all this process happens inside a vacuum chamber. So the primary subsystems of this LIS system are the vacuum system, the vapor generator system, and the ion collection system. So the vacuum system has the function to evacuate the chamber from atmosphere to 10 to the minus 6 millibar vacuum. The vapor generator system comprises of the heaters and the power supplies for the heaters, and the ion collection systems comprises of the ion collector plates and the power supplies for them for applying the potential. Now the control system coordinates the activities of all the systems, so enables the operation of the system from a central point. It enables the logging and monitoring of all the process parameters, and also it ensures the safety through implementing interlocks. So in this talk, I'll be highlighting only one control scenario where we have implemented the ramping
1 minute
up,
left, please.
Yeah, ramping off of the temperature, heater temperature, source temperature, while taking care of the vacuum. So this has enabled us to, the operator saved a lot of time on behalf of the operator, time and effort of the operator, because earlier operators used to increase and decrease the power manually. So this is the control system architecture. On the right side, you can see the PLCs integrated to the field and the control system and the SCADA system implementing the operative station. On the left is the chamber that we have instrumented. Next slide, please. So on the left is the flow chart that shows the heater operation in program mode. Basically, we keep monitoring the vacuum, and if the vacuum goes bad, we hold the ramping of the temperature, and otherwise you continue the ramping. This has helped us in expediting the process. So on the top is the PLC function blocks. There is PID block and ramping block. The ramping block takes input, the vacuum as the input, and then based on that, it controls the ramping. So this is the operator screen. Can we go to the next slide, please? And here we can see the trend of the source temperature while during the experiment. We went up to 850 degrees Celsius. The control was very good in plus minus 1 degree Celsius range. And on the right, you can see the operation screen implemented in SCADA. Thank you.
I just have one question.
Yes, sir.
Suppose I want to have this temperature control below plus minus 1 degree, what I should do?
So PID control suffices. It also depends on what kind of system you have. If it's a lag system, it's very difficult to control. But generally for a good system, PID control is sufficient.
But I guess thermal time constant is very large.
No,
whether it is possible.
Yeah, with PID, if the lags are very large, we can go for adaptive controls also.
Okay.
Okay, thank you.
Thank you.
Now our next speaker is Mr. Subra Prakash Dey, paper ID 1089.
reply दिया
नहीं वो कंट्रोल पे ही बात कर रहे हैं क्लैरिटी नहीं बता रहे
So now 3 minutes for presentation.
On behalf of my colleagues, I'll be presenting on the evaluation of pressure profile inside our laser isotope separation process chamber. As an introduction, I just try to put forward why this exercise is actually required. At the left side, I have the schematic, excuse me for the bad voice, LIS system. Primarily, it is an evaporator at the bottom, electron beam or thermal, vapors coming up. Then there is a laser interaction zone. And then the ions are getting collected on the two vertical plates. This is the basic system. The thing is that ions are getting collected as well as neutral also get collected on the collector plate, and that depends on the background pressure. More the background pressure, more is the collisional scattering and the product gets diluted. The thing is, beyond these, some layers are there. First layer is to protect the vapor from going to the other part of the chamber. There is something called recycle structure, just enveloping the vapor. Beyond that, we also have many other like a hot zone or something. So what happens is that when you are evacuating the chamber, it is possible that the conductance is so low that inside that the pressure will be much higher than what we are expecting. So, and the temperature is higher here. So always we cannot actually measure the pressure inside, which unknowingly will degrade the product. Next slide, please. We had to go for an experimental as well as simulated experiment. So to know what actually is the prevailing pressure. Here I will mention that the pressure requirement is the range of better -6, 1 to -6 or little better in that range. So this is the experimental system quickly describing the thing that there is the major part here is that one gauge we have put directly inside the chamber and one gauge is put outside. That inside is directly connected to what is I'm calling the recycle structure is the processing zone. And there is a calibrated leak that has been put inside. Our purpose is to check the pressure on these two gauges. What is the difference? Ideally, they should be same. What is the difference? Whether there is difference or not, a different leak rate. We have done for 5, 6 leak rate. I have just provided one at the green part below. This is 2.5 into, no, please keep it at the same slide. Same slide. Yeah, thank you. So 2.5 into -2 leak rate, what I'm seeing is that chamber pressure, what we actually measure in any process is 3.8 into -5. And recycle structure pressure becomes 1.2 into -4. So the difference is more than 3 times. Substantial difference which actually was unnoticed. Next slide, please. So we put it, this same system, we put it for simulation. This simulation is done in a Monte Carlo simulation, test particle Monte Carlo software mole flow developed by CERN. This experiment was done at the atmospheric temperature, so simulation also is done. Roughly 5 million particle, and after 8 hours of run. This the right side is the figure which gives the pressure profile from bottom to top of the A and B, or the bottom part is depicted at the left, and that B marked in the left side figure that is at the right. What you see is that there is a sudden jump once it goes inside the recycle structure where the processing zone, the pressure is jumping.
Thank you. Time is over now. So any questions from audience side or live?
Okay, please keep it to the next slide. I'm not going to. Okay.
Yeah, in the first slide, you had shown electron trajectory. Do you also have only electrostatic forces, or there is some magnetic field also?
As of now, it is only electrostatic field, sir.
Electrostatic. So that trajectory should be very accurate, otherwise it would go and hit somewhere else.
No, we have many. First of all, the field is directed, and then we also use some kind of collimating approach so that the ions will be guided and they are not able to go. And our zone, laser interaction zone itself is not very big. It is 30 to 40 millimeter. And the collector plates are at least 3 times bigger than that. We are able to collect most of them.
No chance of hitting the collector.
First of all, ion current is very low, what we are getting. Even if it is hitting, it is loss for us, but it is not going to heat something and heat up or some other things. That it is a loss of the product, sir.
Okay, so time over. Thank you.
Thank you very much.
Now our next speaker is Mr. Dilip Kumar V.
Yeah,
Paper
okay,
ID 1090. Can you hear me?
Slides? Yeah, sure, I'm able to hear.
Yes. So we are
Yeah.
loading your presentation.
Sure.
Arka? Yeah.
Yes,
So your
good
time
afternoon to all.
start now. 3 minutes, please.
Sure. Oh, okay, sir. Good afternoon to all. I'm Dilip. I will be, as the title suggests, I will be presenting the details on the use of residual gas analyzer in a high vacuum chamber, ultra high vacuum chamber, which is used for laser isotope separation. So apart from the use of, can you go to the next slide? You can skip this slide. You can go to the third slide.
Next.
Yeah, sure. So apart from the conventional use of residual gas analyzer for ensuring the leak tightness of a system, as well as determining the gas evolved in the system during the process, we have used it as a tool for analyzing the reason for observed variation in the operation flux during of samarium. Actually, here in this case, we are using samarium as the metal for laser isotope separation. Medical isotope separation. So here, when we have observed some difference in the operation rate of samarium during multiple batches of the runs. So for this, what we have done is that we have determined the baseline trend in the chamber at the operating temperature, which is supposed to be for useful for operation samarium, which is 800 Celsius, without the charge, and the crucible was heated to 800 Celsius, and the baseline trend was determined. As expected, the baseline trend was dominated by moisture, and this was used for comparing with the next set of friends with samarium. So the first slide, the first figure what you are able to see is that it was showing with samarium at 800 Celsius for 1 hour of operation, we could see hydrogen was evolving in the chamber. So the reason for this hydrogen evolution was slightly confusing for us. Why it has caused? What was the reason for why the reaction product of hydrogen has evolved during that evaporation process? So when the experiment was repeated for the next time, the hydrogen level was coming down, and the reaction product was coming down, as well as the evaporation flux was coming down. And on analysis during the after the first experiment, we could find that samarium oxide layer was forming on the samarium metal. So this samarium oxide might be formed due to the process which earlier speaker Anik has mentioned. The hot metal, when samarium was reacting with moisture, and which was releasing hydrogen as a reaction product, and metal was getting oxide. The samarium oxide was forming on the surface. So the samarium oxide,
Okay,
which
1
was
minute
there on
left,
the
please.
so the samarium oxide actually was restricting the evolution of samarium flux from the surface. So this was verified with the third experiment. Even though reaction rate was less, where hydrogen level was less, but still total throughput was reduced. So from the usefulness of this study was that we were able to suggest that we need to remove that oxide layer from the surface after every batch of experiment for getting a consistent throughput for the separation process. If the throughput is reduced with respect to multiple batches, our quality of the yield also will be reduced. So this was the usefulness of the study, by which we were able to justify the reason for which justify the reason for the reduction in the evaporation rate, as well as the evolution of samarium oxide on the surface. Thank you, sir. That's it. Okay.
Now it is time for questions from audience. Any questions, please, from audience side? Okay, so there are no questions. So thank you.
Thank you.
Now our next speaker is Ramchandra Das, 1082. Ramesh Chandra Das, sorry.
ये कौन सा हेडिंग है पेपर
1082 Dr. Ramesh Chandra Das. Yes. So please start. You have 3 minutes from now.
Good afternoon. My title is this time applied mass spectrometry based resonance ionization mass spectrometry setup and related applications. Next. This a time applied mass spectrometry is indigenously developed and it is installed as part of resonance ionization mass spectrometry setup. Time applied is like any other mass spectrometers, but inherent to this specialty is this mass is dependent on time. So using this principle, this instrument is developed. So here we are able to separate individual isotopes, and it can go to a very high temperature like 2000, and it's highly sensitive. And this I have done the simulation of this mass spectrum using Symposium. One can do so with one cannot do so with just basic equations. So this is one of the simulated best simulator spectra of YB. It shows the time evolution as well as the spectra is very well matched. And the various parameters of the mass spectrometer is understood and realized. The another thing is that during our experiment we saw a very unknown peak which was saturating our signal, and that we identified as the from the O1 collimator, so that we rectified. Next. Finally, we have done isotope selective photoionization, and this is a scheme. And I am showing one spectra for 174, which is a very well separated and with very good SNR, and having around 100% selectivity. And similar selectivity we have realized in our actual experiment, about 98%.
Okay, you have 1 minute now.
Thank you. Thank you. I have completed. Next slide.
Now, any questions from audience, please? Or online questions? Okay, so thank you. Now our next speaker is Mr. Rahim N. Rajan, paper ID 1091. Mr. Rahim Rajan, can you hear me? (1091), paper ID 1091, Mr. Rahim Rajan.
Hello.
Mr. Rahim, can you hear me?
Yes.
Yeah. So your paper, please start presentation. You have 3 minutes from now.
Okay.
Please.
I'm Rahim. I will be speaking on the thermal optimization of electron beam, which is used in industrial RF accelerator. In these accelerators, we need typically around 300 milliampere at the output. And for the injection, since the cavity is rejecting most of the electrons, we need to inject at least an ampere of current. So we are using lanthanum hexaborate as the cathode. But in our experience, we have found that the cathode is withstanding without any problem, but in around 500 hours, the filament breaks. So this paper is all about the investigation of about the reason behind this failure. Next slide, please. So to understand this, let us first see the geometry. In the traditional design, there is a Venelt cup which you can see at the towards the top at the left. The lanthanum hexaborate pellet is attached at the middle of this Venelt, and it is heated with a filament, tungsten filament, which is located at 1 mm behind it, and the energy is transferred by means of radiated heat transfer. So at the right, you can see a COMSOL simulation, and we can find that the filament temperature reaches up to 3500 Kelvin, while the cathode and the Venel temperature reaches only up to 700 Kelvin for an input power of 25 watts. This is because the whole power is eaten by the Venel and transferred to the body of the gun. So to solve this problem, let us provide a small annulus gap between the cathode and the rest of the structure in the Venel. Next slide, please. So this simulation shows on the thermal distribution with a gap between the cathode and the Venel. So here we can immediately observe the cathode temperature has increased from 700 Kelvin to 1200 Kelvin, but the filament temperature still hovers around 3500 Kelvin. So to reduce the temperature of filament, we can go for a conductive heat transfer. Can you go to the next slide, please? So in this simulation, the filament is brought closer.
You have 1 minute now.
The filament is brought in touch with the cathode and separated by a thin layer of thermal conductive but electrically insulating film. So here the cathode cathode temperatures rises to 1575 Kelvin, and the filament temperature also very close to that. So the conductive heat transfer to the cathode is the answer to the problem. So at the same time, this structure do not show other losses in the structure which is used to support the filament, the cathode assembly, etc. But still, we can achieve better results with this. Thank you.
Okay, so any questions from audience now?
Yeah, Rahim Rajan, one query.
Yes.
The whole idea was to have high filament temperatures to achieve the current that you need. Now you have reduced this temperature. How will it affect overall performance?
Since the filament temperature reduces, the filament fusing will not happen. So the life of the cathode assembly will increase.
So the filament temperature needs to be is now most optimal. 15.
Yeah, previously it was rising to 3500 Kelvin, which is very close to the melting point of tungsten. Once the temperature is rising, the life will go down.
Okay, so thank you, Mr. Rahim Rajan. Now we move on to next speaker, Mr. Vijay Sharma, paper ID 1097. Yes, so Mr. Sharma, now you have 3 minutes for presentation. Your time starts now.
Please go to the next slide. Actually, it is all about electron gun heating. The electron gun heating is generally considered the life has to be kept sufficiently large. It should be heated gradually, especially it has to go to say power, large power heating. So here what has been done, an automated arrangement has been made so that the power of a non-linear resistance is raised linearly. Basically the power is a function of is actually V square upon R, but the R for a filament dynamically varies up to 10 times, nearly 10 times from cold to hot condition. So here this power supply has been developed such that there is a single phase single phase auto transformer which has increment decrement of voltage, where voltage and current both can be monitored. So since voltage and current can be monitored, we can dynamically calculate the value of resistance and we can dynamically calculate the value of power fed to the filament. We can come to the next slide. Oh, this is the old slide. Which means yeah. So here this is the front end of the power supply control. Here we can feed the value of voltage we want to go to. There is a limit. We can go set the current that is maximum limit and the power. So here the concept here is
you set the power you want to go to say 200 watt and you set the rate of change. For example, 1 watt every 4 seconds. So now it will keep on setting the wattage every 4 seconds, say 1 watt, 2 watt and so on. And the voltage will be try to adjust so that it tries to achieve the intermediate target. Say 1 watt, it will achieve the 1 watt. After 4 seconds, it will change to 2 watt. You try to achieve the next target of 2 watt. So this way we will see the change is linear change and the power is ramping up linearly, though the voltage changing very regularly. But it is trying to maintain the temperature rise, basically the power rise, very linear. So that way we can keep the unnecessary heating very limited. It will be very linear operation. So for this entire operation, there are two modes of operation provided.
You have 1 more minute.
Yeah, there is an auto mode of operation, there is a manual mode of operation. In auto mode of operation, we can come down to this page and there is a you just set the power you want to go to, and this will show the actual power, and just set the start button. The moment you set the start button, you start setting the step level, basically the intermediate power levels, 1 watt, 2 watt and so on. And this machine will automatically try to achieve those intermediate level till it reaches to the final value. So this way, this becomes a very simple one button operation to heat up the gun uniformly, linearly for a given period of time. That's it.
Okay, thank you, Mr. Vijay Sharma. Now it is time for question answers from audience or online questions.
I'll ask Vijay.
Yes.
This your feedback frame time is controlled by temperature or power?
It is controlled by voltage and current only. Temperature is not
temperature is not considered.
Not considered. Because temperature is going 1200, it cannot be measured inside the vacuum.
Was it better to have a current controlled supply for such application than a voltage control?
Either way, it's okay. Actually, it is not voltage current control, it is power control. So that is the correct way. We are monitoring V and I in real time, and we are trying to control the voltage. So finally, it's the power control, which is the primary function.
Okay, Mr. Vijay Sharma, thank you. Now let us move on to paper ID 1054. Ranjit Kumar. Last, but there is one oral presentation. So विजय एक ओरल वहाँ होगा। ये अमिताभ राय आया था यहाँ पे देने के लिए। ये अमिताभ राय को बोले जिसका ओरल प्रेजेंटेशन 15 मिनट तक।
लास्ट में करेंगे ना, एंड ऑफ द डे
ये दिलीप कुमार का हुआ
वो सेशन क्यों वेस्ट होना, क्यों खराब करेंगे?
सुकृति का नहीं हुआ,
दो बार ट्राई किया।
दिलीप कुमार का
सेशन शुरू हो रहा है। ठीक है, हो गया ना। ठीक है, वो क्या पेपर आईडी क्या है आपका?
अमिताभ को एक बार बोला
वहाँ तो दिखा था ना।
Okay, so could we load it?
Sir, shall I start?
Yeah.
Okay. My presentation is about the development of a disk capacitor based mass generator, which is of 30 kV rating, and we have developed a disk capacitor. Actually, we are not able to see here. My slide is missing. We have indigenously developed a disk capacitor, which is rated for 6 nanofarad and 30 kV DC. That is vacuum casted, and its diameter is 600 mm. We'll use it to make a max generator up to 600 kV open circuit voltage, and it will be matched voltage. Its match voltage will be around 420 kV. This will be giving a 25 to 30 nanosecond pulse duration, 4.5 kiloampere current, 4.2 kiloampere currents. This will be applicable for generation of microwave, generation of X-ray.
and my slide is missing. So
this is the APN.
until we have tested it up to 88 kV output voltage, and charging was around 13 to 15 kV.
You are talking about capacitor, na?
Yes, sir.
तो अलग है कुछ लिख रहा है.
ये capacitor, why you need to this capacitor to be encapsulated?
Actually, sir, what we have energy storage capacitors, and these capacitors of ceramic that are in small sizes. What we have to do, we have reduced the inductance of our system Marx generator. So we have distributed a flat disk capacitor. It is 600 mm dia. It is a disk, and we have actually designed according to our user requirement, so that our total inductance of the Marx generator will be reduced, because it will get a coaxial geometry to discharge the current. So we'll get a very reduced inductance as we right now we are using. In that case, we are getting a very good output. So across the load, the output voltage is increased, and we'll apply it for flash X-ray generation. That will be applicable for various strategic and non-strategic purposes.
Okay, thank you. So, any questions from audience?
In terms of the life, if you compare to hybrid capacitor, what is the difference?
What, sir? I'm not getting your question.
Life comparison with the available market.
Life? What, sir?
Life of the capacitor.
Actually, it depends upon the currents and how.
If you compare from the market, available capacitor.
Actually, this is not available in market, sir.
I know.
Yes, sir.
To compare the capacitors life available in market in this capacitor. दोनों का comparison.
Okay, so thank you.
Actually, I don't have that much comparison because I have not seen this type of capacitor. Yes, sir.
This is Sukriti Hertz.
Thank you.
Sukriti is there.
067. Sukriti, can you hear me? Sukriti, can you hear me? Next presentation, Sukriti Hertz. Paper ID 1067.
1067 है ना?
Yes.
1067 है.
Sukriti Hertz, can you hear me?
आया तो कुछ नहीं, अच्छा ये तो आपने डिस्प्ले आगे बता दीजिए, मतलब वो नेक्स्ट स्लाइड देखिए, हम लोग देख लेंगे, देख के कर लेंगे. Let her not present. We'll give marks. The presentation.
Sukriti Hertz.
So it's not available. I think आप ही दिखा दो.
Okay, so we can just slides. Time starts now. 3 minutes. We can wind up in 2 minutes. And we will give full time. Okay, 3 minutes.
ठीक है. Atomic force magnetometer है. There is an influence. Okay, इससे कुछ
सिमुलेशन पे है शायद मोस्टली.
ठीक है. ठीक है सर. दूसरा बेसिकली स्पटर बेस्ड आयन सोर्स है. This is what I can understand. Next में आएंगे. बनाया
लास्ट PPTs.
कुछ सिमुलेशंस हैं ज्यादातर. ठीक है.
सिमुलेशन पे है मोस्टली.
Thank you.
Okay, so thank you. Let us conclude the session and draw management comment. Yeah?
Vishnu.
अच्छा ठीक है. Okay.
Paper ID क्या?
What is his paper ID?
1150.
Okay, so next speaker is
Vishnu Sharma.
Shall I start, sir? Sir, my topic is design. 1150, sir.
paper ID 1150. Vishnu Sharma.
Yes, sir.
Your time starts now. 3 minutes.
So, sir, my topic is design and development of magnetic system for backward wave oscillator. Sir, next slide, please.
So BWO is basically a vacuum device that is used to generate microwave of gigahertz order. So in this schematic, the basic diagram of the BWO system is explained. In BWO, when we give the high voltage pulse to the cathode of the BWO, electron beam generates, and that passes through the slow wave structure of the BWO that generates the microwave. So for this thing, we have to apply a specific magnetic field in the BWO region, which is generated by the magnetic coil, and that magnetic coil is energized through the energy storage capacitor. And this schematic diagram shows the electrical circuit of that. Next slide, please, sir. So there are two main parts of the magnetic system: magnetic coil and the capacitor bank. So for magnetic coil, to calculate the magnetic field for any magnetic coil, we use these three equations, which is derived from the Biot-Savart law, and then we write a code in the MATLAB which gives the total magnetic field of the any coil. So based on that, we have optimized a magnetic coil for the X-band region. So the cross-section area of the magnetic coil is decided by the skin depth, and the maximum current is decided by the maximum current density that is allowable in the system. And with several iterations, we reached at this optimized solution. The next slide, please. And this, the second part is the energy storage capacitor, and we see that some residual energy is left when the maximum current reach. So due to that thing, we have to store some extra energy in the energy storage capacitor, and that's why the we cannot transfer all the energy, and we have to feed some extra energy in the capacitor. And this curve shows the capacitance and the efficiency of the charging voltage capacitor. And this is the diagram of the capacitor which is used in for the BWO. Next slide, please, sir. So these are the conclusion. The MATLAB code was written, the magnetic coil was designed and developed, capacitor bank.
Okay, so your time stops now. Any questions, please?
Only one question. In this solenoid coil, backing iron.
Okay.
Outside backing iron, you can increase the field. And with the iron, if you use parameter, why you are not using? What disadvantages of
the iron can reduce the fringe effect.
कम हो जाएगी अब हो जाएगा 15
हाँ योग हम यूज कर सकते हैं, लेकिन सिस्टम थोड़ा बड़ा हो जाता है और हमको उसको
Okay, so thank you. Let us conclude the session. And from management committee, there is a small memento to judges. Yes.
Don't mind question. Question